Hi, welcome to Earth and Environmental Science video lecture number 1. This is Miss Machula, and this unit we're going to be talking about space. This will be the first video that you have for space, and we have 3 objectives in this video. 3 things that we're going to try to learn, and at the end we'll go back and see if indeed we did learn those things. The first is our North Carolina Standard Course of Study standard, and that is asking us to understand how Earth moves through space in relation to other planets, stars, and galaxies. Our next objective is to develop an understanding of the origin and evolution of the Earth system, and that is one of our national science standards. The last one that we have to look at is the Next Generation Science Standards. And they're asking us to construct an example of the Big Bang Theory based on astronomical evidence of light spectra, motion of distant galaxies, and composition of matter of the universe. It all sounds very confusing. Hopefully I can simplify this for you. We don't need to learn quantum physics or astrophysics to understand this. We can understand very generally the basic motions and functions and theories surrounding this. So let's get started. All right. So we're going to talk about the Big Bang Theory. Let's first remember that what a theory is. Theory it's not as I might use it. I have a theory about why my plant keeps dying. No, a theory in this instance is a scientific theory. And if you remember, these are things that are have a good, strong, foundational truth about it based in math and physics. And it remains a theory until someone can prove it not a theory, can prove it false. So we have the theory of gravity, and no one has been able to say that it doesn't act and function in the way in which the theory of gravity indicates that it does. So these are pretty strong indications, and they're not easily changed. So let's look at this Big Bang Theory. It was first proposed by a Belgian Catholic priest. His name, and I'll try to pronounce it correctly, was Georges Lemaitre. And he proposed it in 1927, and we have a picture of him right over here. And he based his work on, he really based it on the work of 2 other men. One of those would be probably familiar to you. We've got Albert Einstein here, and one other man, William de Sitter, not quite as famous as Einstein. But so what did this theory say, and how did we figure it out? Well, to figure it out, we actually worked backwards. We started here today. And what we have noticed through our observations and recordings of use of scientific instruments is that galaxies are moving away from each other. So they are expanding. And we're going to talk about how we figured that out later. But if they're expanding, then if we were to play this video backwards and run these galaxies in reverse so that they're not expanding but they're contracting, that if you run that back to its theoretical beginning, they would all contract into a singular space. And this is called the singularity. And we don't know what came before this singularity, and we don't even know what caused it to explode, or not explode, but to inflate. We have this, or to expand, this Big Bang event. It wasn't a bang. There was no air at at the Big Bang expansion, so there couldn't be a sound. But we call it the Big Bang. And what happened is that when this singular event occurred, we had a rapid expansion, or this section, or this unit of time is called inflation. It was, and it lasted for a very, very short amount of time, just very small part of a second. Um, there was a period of time that, and this was chaotic here, but there was a period of time when it slowed down a little bit, and then it started to speed back up. We're still expanding. As you can see, it gets bigger and bigger, and these galaxies are moving further and further away from each other as time goes. And knowing the rate of expansion and measurements that have been made over many years, we can extrapolate from that how old the universe is. And so they've done these measurements and have come up with, if we go from where we are today and calculate all the way back to this singularity, we have the universe's age at 14 billion years ago. So that's kind of in a nutshell what the Big Bang Theory is. Let's talk a little bit more. I have a great next image for you to look at that might help a little bit. So as I said before, so we've got the Big Bang over here, and I said these kind of images right here all occurred in this chaotic period. It was 10 billion degrees Fahrenheit, and you had all of these things like matter and antimatter canceling each other out. You had quarks and neutrinos, all these kind of words that you've heard and maybe didn't know what they were. They were kind of the precursors to our atom. In here we had neutrons and electrons and protons that weren't organized, and these things were all just interacting with each other in a very short amount of time. So, I mean, as you see over here, we have time equals 10 to the minus 10 seconds. So that's a fraction of a fraction of a fraction of a second. And that's when, so the first, seconds, all of this is occurring. And then about 300,000 years, they organized over a period of time, and they formed these neutrons and protons and electrons formed our first neutral atoms. If you remember our cosmic timeline event, that was one of our items on that timeline were these neutral atoms. And when they formed, we suddenly had light. So light was formed. And we recently have been able to, since there was light, have been able to measure this thing called cosmic microwave background radiation. And it is really, it's electromagnetic radiation kind of remnants from the Big Bang. And it's really heat left over from it. And we're able to measure it. About this same time, or when the four fundamental forces of nature, these things that are the basics of physics, were first kind of organized. We had, gravity, magnetism. We had the weak interactions between atomic particles, and we had strong interactions between atomic particles. Everything that physics and chemistry are based on. And so from that time, if you remember our cosmic timeline, we had the galaxies or the planets start to form and galaxies organize and all of these things going on. And then really right here at today is where everything we know, all of man on Earth, all of life on Earth has occurred. And so, this is our billions of years that we talked about over here, our 14 billion years to go from the Big Bang to today. Okay. I want to talk a little bit about this cosmic microwave background radiation. You might ask, how do we know that? Because this is really a picture of our universe and how we kind of have figured some of these things out. We have instruments and telescopes that can take pictures in different parts of the light spectrum, whether it's in visible light or microwave or infrared. And so this is microwave photograph that was made. And you might wonder, well, how did we do that? Well, it was actually made, or the data was acquired through a satellite that was sent out by the European Space Agency. And this was the Planck satellite. This is the one that's responsible for it. It has done a myriad of different readings and photographs as it's moved through space. And this image just came about in 2013. So we are, this is still a new field. We're learning more and more about the universe and are being able to actually visualize it better based on some of these technologies that are being developed. One of the interesting things to me is that as we've really kind of mapped the universe, we have found out that only about 5% of the universe is made up of matter, like planets and stars and galaxies, things that are tangible to us. Everything else is something that's called dark matter and dark energy, and there's so much research and investigation going on in those fields now. It's really ripe for discoveries. Okay, so if we go back to this first picture and where we started, how did we know this Big Bang? And we talked about these galaxies moving further and further away from each other. So how did we figure that out? Because we didn't just look at our next door neighbor galaxy and say, wow, look at there, it's moving further and further apart. That's not how we do it. So we have telescopes that can take images in different parts of the spectrum. And this part that we're going to look at is called the visible light spectrum. That's your Roy G. Biv, if you remember that, red, orange, yellow, green, blue, indigo, and violet. And that's your visible spectrum. And so what happens is when we're looking at a galaxy through a telescope, and we're looking at this galaxy, and we're taking readings in this visible light spectrum, and let's say we might have a normal kind of a full visible light spectrum, if it included everything, might look like this. Okay. Well, as we are, if we're looking at this, and if it's moving away from us, then it's going to expand or stretch that light, that wavelength. And it's going to stretch it over here into the red part of the visible spectrum. And this is called redshift. And redshift is one of the key things that lets us know that our galaxy, all of these different galaxies, are moving further and further away. We've taken many pictures of galaxies, and redshift is seen in almost all of them. Conversely, there are a few little oddities where galaxies that are close to us are actually maybe moving a little bit closer. So as a galaxy is moving close to us, it would compress that wavelength, and it would compress it down here into the blue end of the visible light spectrum, and that way we would know that it's moving towards us. So that's how we figured it out, that galaxies were moving further and further away. It's as simple as that. The photographs of these galaxies had the light waves were stretched into the red and called a redshift, and told us that they were the galaxies were expanding. All right, so I hope that kind of gives you a general idea of the theory of the Big Bang and expansion of the universe, and it's still expanding. And we're going to investigate that a little more in a lab that we'll have in class. All right, now we're going to talk about some movements a little closer to home. And we're going to investigate this fella called Johannes Kepler. He was a German astronomer, 1571 to 1630. And you can see one of his quotes here. He says, "I much prefer the sharpest criticism of a single intelligent man to the thoughtless approval of the masses." So that should tell you something about his nature. He valued, obviously, people who were knowledgeable and may disagree with him based on facts and evidence. Okay, so Johannes Kepler is responsible for Kepler's laws of planetary motion, and there are 3 of them. Our first law is that all planets move around the sun in elliptical orbits, and they have the sun as one of the foci. So no, the sun isn't the center or in the center of our solar system. It is off to one side, and planets are going to orbit the sun in an ellipsis. So at some point they're going to be closer to the sun, and at another point in the orbit around the sun they'll be further away. So this first law is that they orbit around the sun in an elliptical orbit, where having the sun as one of the foci. Okay, that one's kind of straightforward. The next one is a little more difficult. So Kepler's second law of planetary motion. It states that a radius vector joining any planet to the sun sweeps out equal areas in equal lengths of time. Well, we could probably figure that out if we kind of studied that sentence, but it's basically saying that planets revolve around the sun at varying speeds. So if we look at a body that's moving around the sun, say we're talking about the Earth, we have a greater distance here, right? So as we are closer to the sun, we're moving quicker, right? And in a month, we're going to span this amount of space. When we're further away, we're going to be moving a little slower, and we'll only span in a month this amount of space. Well, what Kepler's second law of planetary motion says is that this area that is in here will be equal to this area, so that A1 equals A2. We'll move quicker when we're closer and slower when we're further away, but the area will still be the same. So that's Kepler's second law. The third law states that the squares of the sidereal periods P of the planets are directly proportional to the cubes of their mean distances D from the sun. Yeah. Okay, so that means the time it takes for a planet to orbit is proportional to its distance. And you can see all of this has been calculated. But basically what we're talking about here is that we have all of these planets orbiting the sun. Those that are closer to the sun, such as Mercury, can make their orbit in about 88 days, 88 Earth days. Here we have the Earth. It's making its orbit in 365 days. That's a year. And then if you go further out, say to Neptune, it takes 60,190 Earth days to make its full orbit. So the third law is the time it takes for a planet to orbit is proportional to its distance. So those are your 3 laws of planetary motion according to Kepler. And so let's move on now to the hierarchy of the universe. Well, what does that word hierarchy mean? Well, hierarchy is a system or organization in which objects are ranked one above the other, and each object is going to be linked to the objects under it. So it's kind of like if you have a hierarchy in in a ruling class, you'd have the queen, and then you might have the dukes and duchesses, and then further down the line, you end up where we are as the peasants. It's a hierarchy. And so the first one is going to be the universe is made up of galaxies. So if I have a universe, just kind of draw a little picture here. So here's our universe, and inside of that is billions and billions and billions of universes. I mean galaxies. All right. And if I were to then take one of these galaxies, our next step down is going to be galaxies are made up of stars and star systems. So inside of this galaxy is full of stars and star systems. We have three different types or shapes of these types of galaxies. We have spiral, we have elliptical, and we have irregular. And the Milky Way is a spiral one. The next one that we have, if we were to take one of these, we would have, we're going to have a star system, right? And it's going to have planets that orbit around it. Pretty bad drawing. Okay, and so we would have star systems, and they are made up of planets. And then finally, if we were to take one of these planets, let's say it's Earth, planets may have satellites or moons that orbit around them. So here we have some examples. Here we have our universe full of galaxies. Then galaxies, the different shapes, and inside of those we have star systems. And then inside of those we have planets that may have satellites or moons that orbit them. So that's your hierarchy of the universe. Okay, our next bit is an intro into, I want to show you the kind of the intro into the movie Contact. If you ever get an opportunity to watch it, it's a great movie, stars Jodie Foster. As it plays, let's just remember, kind of review some of our middle school astronomy. So this is our solar system. So we have the sun. Then we have our rocky planets. Then we have the asteroid belt. We have our gas giants. We have the Kuiper belt. And we have the Oort cloud. All right. I'm going to pause for a moment, plug in my computer before I play this. I'll be right back. Okay. All right, so as we watch this little movie clip, I want you to think about this sequence. This is what you're going to be seeing. It's going to start with Earth, and it's going to move back. It's going to back away from it, and it's going to move throughout this towards the edge of the universe. You'll go past the planets. You'll go through the asteroid belt. You'll go through the gas giants, through the Kuiper belt, the Oort cloud. It will show you a nearby nebula, the Eagle Nebula, and then it will back on out. You'll see the Milky Way galaxy. You'll go through the center of another galaxy until it keeps backing away towards the edge of the universe, and you'll see billions and billions of galaxies. Okay. Okay, so I hope that kind of helped give you a perspective of the size of the universe. Okay, let's talk a little bit more about movements that the Earth makes. There are two very important terms here that you need to remember and understand the difference between them. We have rotation and revolution, and we're talking about these are movements of Earth. So rotation is the movement of Earth on its axis. So if we have the axis here. Remember, that's the North and the South Pole, right? North and South Pole. And here's Earth, and it's the movement of Earth on its axis. So it spins. If we have the sun here, and let's say we're located right here, here we have day, and as it turns around to this side, as the Earth spins or rotates on its axis, when we're over here, now it's night, come around and we're day. So one full spin is going to be 24 hours, right? And the way to remember that rotation is about spinning of the Earth on its axis. Well, here's a little trick. It's got an A in it. So axis. Rotation is axis. The other movement is called revolution. And this is going to be the movement of the Earth around the sun. So if you remember, we've got the Earth and we've got our orbit. And here's Earth around the sun. And it's moving around. So we know that that takes one full trip is 365 days or 1 year. And this is called revolution. The little trick here to remember that it's around the sun, it's got a U in it, so sun. So we've got rotation axis, revolution sun. Just a couple little tricks to remember that. It's very important that you remember the difference between the two. Okay. Now we talk about a few more movements of Earth. We have these two words over here, two more words for our vocabulary, aphelion and perihelion. And so we're talking about helion here. We're really looking at the root of that, and the root of it is helios. And that is Greek for the Greek god of the sun. That's where the word helion or helios comes from. And so this has to do with, you've got Earth orbiting around the sun. And it really has to do when Earth is at its farthest from the sun in its orbit. So we're kind of make that better. At its farthest point. And this actually occurs in July of every year. And then we have this other word, perihelion. And as you might guess, if we have the sun, we have our orbit. It's when it's closest, when Earth is closest to the sun. And believe it or not, this takes place in January. You might be thinking, wait a second. If we're closer to the sun, we should be warmer. If we're further away from the sun, we should be colder. So that should be January and that should be July. Nope. Remember, temperature is going to have to do with something completely different, which we'll learn in our next video. The elliptical orbit is drawn here very exaggerated to help kind of visualize it. But really the difference is very small, and there's no effect on temperature based on it. So it's just when it occurs. So a way to remember these, I have a little trick for that. If we have aphelion, it's afar. So the Earth is afar from the sun. Perihelion, you can laugh at this one. Peri sounds like very. So perihelion is when it's very close to the sun. And just a little trick to remember those. All right. Aphelion and perihelion. All right, these next two words we have, precession and nutation, are probably the most complicated thing you'll need to try and understand. And we'll look at this in class as well with some models, but let me try and explain it. These are movements of the Earth as it moves through space. And this one called precession is the change in the direction of the rotational axis of a rotating body. So here's our axis, our rotational axis, and here's our rotating body, right? We said day and night, day and night. But what happens over time is that this Earth really kind of moves like a top. It's spinning, but then it kind of gyrates around in a circle. And it creates this precession, this circle up here. Well, if we went out tonight and looked due north, we would see the North Star, the star that people navigate by because it stays at that space in the sky as other stars move around. But it's what happens though is we've got 26,000 years. This axis, as it's moving in this circle, takes 26,000 years for it to tilt the other way. Instead of the North Star in the polar north sky, it's going to be Vega, will be our North Star, so to speak. And then in another 26,000 years, it'll come back around, swing back around, and it'll go back to Polaris, the North Star. And this is called precession, this movement. It's the Earth is spinning, 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 but it's also, as a whole system, the axis is actually making a circle. And that's precession. Nutation is, as this is occurring, it's actually kind of wobbling. The axis is wobbling. So this axis of rotation wobbles as it moves, and that's called nutation. And that changes every 18 years. We get a half a degree change, half a degree movement in this wobble. The interesting thing is that this is influenced, this precession is influenced by gravity of the moon and sun. A little bit of the sun, mostly the moon. And it's important to understand that the Earth really isn't a perfect sphere. It's actually, if we have our axis, it's actually kind of an ellipse kind of. And that is that we have this gravitational pull right along the equator. You know, we have a liquid coating to the Earth, and it kind of pulls it out and creates this kind of a bulge. And so that gravity pulls that, and that pulling on the equatorial lines or equatorial area of the Earth is what causes this movement. Additionally, down here, it's influenced by the gravity of the moon, which creates tides, and we'll talk about that in our next video. And that causes that wobbling to go. And so that's precession and nutation. I think models will probably help you kind of visualize that better, and we'll do that in class. All right, the next concept we have to figure out or learn is barycenter. And barycenter is nothing more than, let's say I had a ruler here, and I had two objects of differing mass. One here, let's say this has a huge mass and this has a much smaller mass. Where would you put your finger to balance this ruler so that it stays in this plane? It doesn't tip over and drop them onto the floor. Well, I think you could probably figure out you need to be closer to the one with the bigger mass, right? So your barycenter is nothing more than the point of balance between two objects. So our point of balance between these two objects right here would be right, maybe somewhere about right here. And let's say we can figure this for any kind of bodies. Balls, we can do it for planets, we can do it for all kinds of things. And so in our example, let's just imagine that this is the Earth and this is the Moon. And we're going to figure out the barycenter between these two bodies. Well, there's a couple things you need to know in order to calculate that. You need to know the distance between the first body, the center of the first body, and itself. Well, that's going to be 0, right? The difference between the center of Earth and the center of Earth, there is no difference. Second thing you need to know is the difference between the center of Earth and the center of the Moon, the first body and the second body. And if we're looking at the Earth and the Moon, the distance between the center of the Earth and the center of the Moon is actually 238,855 miles. So we have a number to apply to that. The third piece of information you need to know is the mass of the Earth, or the mass of the first body. And here we have Earth's mass. And then the last and final piece is the mass of the second body. And so we have the mass of the Moon here. So if we wanted to go and calculate that, we could do that. Here's our measurements we know, and we're going to plug them into this formula. This is your barycenter formula. Once you do all of that math, you get, and we're trying to figure out where along this measurement from the center of Earth to the center of the Moon is the balance point. Well, we've determined between Earth and the Moon that the balance point is 4,729.33 kilometers. So if we started here, we'd go that far until we had measured that amount. Well, when we're looking at the Earth and the Moon, the Earth's radius is 6,378.1 kilometers, right? So the radius from the center of the Earth, a radius, right? So that's 6,378.1 kilometers. Well, we've determined that our barycenter right here is only 4,722.33 kilometers. So that's kind of confusing, right? There's a difference here. It's actually somewhere, if this is our radius of Earth, right here, our barycenter is somewhere back here. And actually it's 1,648.77 kilometers inside of the Earth. So if you start at the center of the Earth, or at the edge of the Earth and go towards the center, 1,648.77 kilometers, you will find the point where the balance point. And so when these two bodies are orbiting, we tend to think of the Moon orbiting around the Earth, and we don't tend to think about the Earth doing anything. Actually, the Earth is also orbiting around the barycenter. And so it's moving some as well as the Moon moving around it. We'll also look at another video in class that's a great kind of explanation of that. But you can figure out barycenters for any number of different objects. All right, that's it for this video. These are my two dogs, Ringo and Ollie, and this has been a Ringo and Ollie production. Have a great night.